In this video, we're going to look at Section 8 of the 2018 exam for Math 121. This is where we've been given a table of values, and the units here are megatons of carbon dioxide per year. And then we have a certain number of years and the output of greenhouse gases. We're asked first to use the Trapezoidal Rule to estimate the total carbon dioxide emissions. So total implies an integral here over the period January 1st, 2009 till the end of the period here, marked at the end. Each of these rates are given on January 1st, so what we have is 1 year, 2 year, 3 years, 4 years, 5 years, 6 years, 7 years total span. And what we're being asked to do here is use the Trapezoidal Rule to get a total, so we just think of how the units work out as a guide. We're looking for total carbon dioxide emissions. So total CO2 is going to be something we obtain by adding up the rate in megatons per year times years. Or if you like, in the units of our, or the symbols of this question, it's E of t times delta t. Now in this particular case, all of these intervals happen to be exactly 1 year, which is convenient, and the megatons per year works out perfectly. So if we're looking for the approximate value from the Trapezoidal Rule, the Trapezoidal Rule says take the average of your two rates. So here are 682 and our 694. Divide that by 2. That'll be the average rate of output. And that's over a time span of 1 year. And then we do the same thing again for the 694 and the 700. What's a good representation or a good approximation of the output over this whole year? Well, let's take the value at the start, the value at the end, and average it. Averaging just means adding and dividing by 2 and multiplying that by the time interval. And we do all that all the way to the end until we have our last interval, our 714 and 704. That would be the average output on this interval, but that interval is still 1 year long. And if we reach for our calculator, we end up with a grand total of 4941 megatons. All right. Now, what if we change this up a little bit? Here we're given a formula instead of the data points, and we're told that this formula here is a good approximation to the data. Well, what we want here is the exact version of what we were doing before. So we're going to integrate from 0 to 2009 to 2016 is the endpoint here. That's a total of 7 years. So from time 0, that's 2009, to time 7. And we have this relatively simple quadratic, which is nice. And the integral will be adding up the rate of output or emissions times the units of time. So this is exactly what we did above, only now with a fundamental theorem of calculus. And to do that, we just look at each of these terms, and because they're just powers of t, we just add 1 to the power, divide by the new power. And for the last term, don't forget, if you integrate a constant, you get a constant times t or constant times x, whatever your variable of integration is. And then you sub in the 7, you sub in the 7 here, you sub in the 7 here. At the end of the day, you end up getting 4940.65. And reassuringly, that would be in megatons, that is close to the value, very close to the value, in fact, that we obtained with part A when we used the Trapezoidal Rule on the same problem. So it would have been a bit of a red flag if this was 4,000 and this was 2,000. That would point to one of the values being in error. But here, they agree. That's an excellent sign. Last but not least, we do change gears here. So this requires getting out of the rut that you might be in mentally of thinking everything here is an integral. What this question is asking about is based on the last bit of data. So we were at 714 and then 704 and I believe those are the numbers. Yep, 714 and 704. That was at 2016, January 1st, and 2015. Assuming the trend on that year continues in a linear way, estimate the emissions rate we would expect on January 1st, 2020, so 4 years later. Well, honestly, with these 2 data points here, I think the easiest way to go is to look at a 1-year increase in time resulted in a decrease of emissions by 10 megatons. So we went down by 10 megatons. If we go over 4 more years, well, a pretty reasonable expectation is that we're going to go down by 4 times as much, or 40 megatons. So we would expect that the emissions in the year 2020 would look like 704 minus 40, or 664 megatons. 664 megatons per year, because it's a rate. We could also look at this as a slope calculation or linearization. So we could talk about the slope, which is going to be the change in E over the change in T. That's your end emission minus your start emission, all over the end year minus the start year. And there we get, at the end of the day, our minus 10 slope that we saw here. And then what you can do is use that slope to predict forward. So you can say E of 2020 is going to be approximately E of 2016 plus m times the delta t between them. So that was our 714 plus the slope we just found, and then the time span, which is 4 years. Oh wait, it's the same calculation. And we end up with, 704 is the value at 2016. And then we get the same value of 664 megatons. So I think those are 2 fairly natural approaches. Again, there are some other variations, but based on the wording of the question, assuming that there's a linear trend here, how do you continue a linear trend? Either with a slope line formula or some little sketch of the graph and an indication of the slope. Either way would get you to that answer.